Let's take a look at our questions that we had for homework over the weekend, page 207, number 1 and 2. We're going to do both of them here, starting with number 1. It says two people, A and B, are sitting on a bench this far apart. Here's their masses. We want to find the force of gravity exerted by B on A. Even if we couldn't see the answers down here, we would predict that this is going to be a very, very, very small force, right? How come? Because they have very, very small masses in the grand scheme of things, right? We would say that M1 is 55 kilograms, M2 is 80 kilograms. Anybody do it the other way around? Anybody say M1 was 80? Does it matter? Yeah, it doesn't make any difference. We're going to say something is 0.60 meters. What's that? Yeah, R. Be careful with the term. Let's not say radius, because radius infers a circle. We have two people sitting on a bench here. There's nobody orbiting around the other person. There's no circle here at all. There's just a distance between two people. Now, excuse me, that R could be a radius. The Earth, for a distance away from the sun, that's a radius, because right, that's how far the Earth is away from the sun as it orbits around. But it's not necessarily a radius. We're calculating F here. So we're going to say F is equal to G M1 M2 over R squared. And then there's that constant. It's on your data sheet. M1 is 55, M2 is 80, divided by 0.60 squared. Okay, let's do this on the calculator here. Remember we said when we have a calculation on the bottom, we usually like to do that first. 0.6 squared is equal to 0.36. And then we're going to say 6.67 times 10 to the minus 11 times 55 times 80 divided by that number that we got on the bottom. Gives me 8.15 times 10 to the minus 7. And go figure, that's the answer that's in my book. 8.2 actually, 2 digits, because if you look back to your data here, these are all 2 digits. 8.2 times 10 to the minus 7. How many people got that? Sorry, that shouldn't be meters, that should be newtons, right? So that's pretty straightforward, right? Okay, let's look at number 2. The mass of the Titanic was 4.6 times 10 to the 7. Here's the force of gravity. What's the mass of the iceberg? You see this pretty big here, which we would expect to have that big of a force of gravity. We're going to say M1 is 4.6 times 10 to the 7. We're going to say the force is 61 newtons. We're going to say R is 100 newtons, 100 meters. And we're going to solve for M2 here. Solve for M2. What are we going to take over first? R squared. Now we're going to take over the G and the M1 by dividing. Yeah. And then you sub in your numbers. Get the bottom number first, then get the top, then divide the two, and we should get, when we do that, 2.0 times 10 to the 8 kilograms. All right, what are we going to do? What are we going to do if we have a situation like this? We got an eclipse here. The Earth, the Moon, and the Sun are all lined up in the same plane as shown in the diagram down here. See, the Earth is in between the Moon and the Sun. Now we don't see the Moon, right? Because the Moon is in the shadow of the Earth, right? We know that the force of gravity caused by the Moon on the Earth is enough to keep the Moon in orbit around the Earth. It's also enough to affect the Earth's water, right? You get massive tides. So in some cases, massive tides, like massive shifts in the Earth's ocean because of the Moon's gravitational pull. Well, the sun applies a force of gravity as well. In fact, so big of a force of gravity that keeps the Earth in orbit around the sun. We get two big forces of gravity acting on the Earth here. We want to know, in this situation, when they're all in a line like this, what is the net force of gravity, or the total force of gravity caused by these two things on the Earth? What do you think we're going to do to tackle this? Any ideas? Good. You're going to draw the force diagram, as Patrick called it, or the real name for it, the free body diagram. But you know, we know what you're talking about. There are two forces acting on the Earth right now. There's the force of the moon on the Earth. I'm going to label that this way, because the moon pulls the Earth to the left. I'm going to call that the force of the moon on the Earth. Or maybe we should just call it FM. Let's call it the force caused by the moon on the Earth. What about the sun on the Earth? We'll just call that Fs, as opposed to the force of the sun on the Earth, Fse. The moon pulls the Earth to the left. The sun pulls the Earth to the right. Now, what happens to the moon here? Well, it gets pulled towards the Earth, right? But I don't care. That's not the question. The question is what happens to the Earth. What about the sun? Does the sun get pulled to the left as a result of the Earth? It does, yeah. But we don't really care about that because that's not the question. The question is what happens to the Earth, not what happens to the sun or what happens to the moon. The force of the moon on the Earth, the force of the sun on the Earth. Now, what comes next? We've drawn that force diagram, as Patrick called it, the free body diagram. What comes next? We need to get those forces. We need to get the values of those forces. The force of the moon on the Earth, Fm or Fme, is Gm, force of the moon, mass of the Earth, over r squared. Mass of the moon, we're given that number there, is 7.35 times 10 to the 22. Mass of the Earth is 5.97 times 10 to the 24. Divided by the separation distance, which is the distance from the center of the moon to the center of the Earth. Okay, let's get that number here. Let's get that number. Let's get the bottom number first. 3.84 times 10 to the 8. Let's square that. Okay, there's my bottom number. Now let's get the top number. 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22. Look, the moon is 100 times lighter than the Earth. Like 100 times. 10 to the 22 versus 10 to the 24. Here's the mass of the Earth. Divide that by 3.84 squared, which I had already calculated. Oh, look at that force. The force of the Titanic on the iceberg was 61 newtons. The force of the moon on the Earth is 1.98 times 10 to the 20. Half done. You know what? I'm going to change the color on this one. I'm going to say the force of the sun on the Earth is green. Just so it's a little clearer what we're doing here. Let's say Fs. This is going to be real similar, right? That should be not the mass of the moon and the sun, the mass of the Earth and the sun. Mass of the sun is 1.99 times 10 to the 30. Look at that. 10 to the 30 That's 10 to the 6 times bigger than the mass of the Earth. It's 100,000 times. The sun is 100,000 times heavier than the Earth is, even though it's all made up of gas. Isn't gas lighter? Depends on how much you have, right? If you get enough of it, it's heavier. That's good news. Like, there's a lot of hydrogen gas in the sun, which is good news because we need that nuclear furnace to keep going, and we need lots of hydrogen gas up there to do that, to sustain that. That distance is 1.50 times 10 to the 11. Let's figure out that bottom number. Squared. Okay, let's do the top number. Let's divide it by the bottom number. 3.5218. Which pulls on the Earth more, the Earth or the Sun? Which pulls on the Earth more, the Moon or the Sun? Sun. That's not a big surprise, is it? The Sun is 100,000 times heavier than the mass of the Earth. 10 million times heavier than the Moon. Now, it is also further away, which reduces the force, but not that much further away. Now what? Oh, everybody in this room so knows what to do next. We have so done this so many times. Add them up. F net is the sum of the forces. Fm plus Fs. What do you got to watch out for here? Okay, what's wrong with what I've just done? There's no what? One of them has to be negative. Yeah, one of them has to be negative. Parker, which one should we make negative? Yeah, really, whichever one you want. Yeah, really it is whichever one you want. But which one makes probably the most sense to make negative here? Probably the Moon, because it's acting to the left. But as long as one is positive, one is negative, doesn't really matter. Let's combine these now. .50 times 10 to the 22. All right, let's have a look at a couple questions on page 209 here. I want you to do, for sure, question number 1, and then I want to see what you can do with question number 2. I'm confident that even though we haven't done a question exactly like number 2, that you can do it, but you do have to think a little bit about question number 2, a little bit more than you do about question number 1, all right? Do number 1, and then try to do number 2 after that. So look at question number 1. We want to find the net force of gravity on the Earth here. We know that the Moon pulls on the Earth this way. We'll call that Fm, the force of the Moon on the Earth. We know that the Sun pulls on the Earth this way. We'll call that Fs, the force of the Sun on the Earth. Good? Hey, we already know Fm. We calculated that in the example question. Fm was equal to gm1 m2 over r squared. Same numbers involved here. The force of the Moon, we found in this last question, is gone. Let's go to the unrounded number there, 1.9. Who's got the unrounded number? 1.98483. Okay, that's good enough. Times 10 to the 20. Okay, so that was the force of the Moon on the Earth. Now the force of the sun on the earth, this is just from a previous question, but we can find it, right? If we don't have it written down from the previous question, then all we got to do is multiply g times mass of the sun times the mass of the earth over r squared. What does that one work out to be? Quite a bit bigger, right? Something times 10 to the 22, I think it was. 3.52 times 10 to the 22 newtons. And now, in the last question, when we were analyzing a lunar eclipse, we had to make the force of the moon a negative value. When we're analyzing the solar eclipse, we're making them both positive because they're both to the right. Fm plus Fs. Add them up, and when we do that, we should get the answer that's given to us in our book here, which is 3.54 times 10 to the 22 newtons. Positive, so it's toward the sun. So that's a bigger number than we had before. Why? Remember we had 3.50, I think it was, times 10 to the 22? Now it's 3.54. Why is this one bigger? Yeah, because the Earth and the Moon are helping each other out now, as opposed to opposing each other like they were in that last example. When do you think you get the strongest tides? The highest tides? You'd be more likely to get high tides, really high tides, here, right? Because that force of gravity acting on the Earth and the water, that fluid on the Earth, is stronger here than it would be if the Moon and the Sun were on opposite sides of the Earth. Good? Like, the difference is not that huge, 3.50 versus 3.54, but it's bigger, measurably bigger. Okay, give you another minute or so to work on number 2, and then we'll take a look at that one. Taking a look at number 2 now. It says during the first quarter phase of the Moon, Earth, Moon, and the Sun are positioned as shown in diagram figure 4.22. Calculate the net force exerted by both the Moon and the Sun on the Earth. Just like the last question, except this time the Moon and the Sun and the Earth aren't in a straight line like they were in that last question. Look, we want to find the force of gravity on the Earth caused by the Moon and the Sun. Let's draw each of those forces. Here's my free body diagram. The force of the Moon, this way. We know its value, right? It's 1.984837 times 10 to the 20 newtons. There's no point in me calculating that value again. I already know it because the numbers are the same. Now the Sun pulls the Earth this way, to the right. I'm going to call that Fs, the force of the Sun on the Earth, and we know its value because the numbers are the same as the last two questions. 3.5218489 times 10 to the 22 newtons. Now, how are we going to combine these? Patrick, I'm going to ask you, because we chatted about this earlier on. How are we going to combine these two numbers? Yeah, so in order to get R, we have to draw a vector diagram, right? And vector diagrams have to be drawn head to tail, right? So this isn't good enough just to say this and then connect the dots there, join the lines there. We want to say this one is to the right, this one is up. That's drawn head to tail. And then my resultant vector, my net force, is this way. So in order to figure this out, I'm going to label this 3.5218489 times 10 to the 22. I'll label this one 1.984837 times 10 to the 20 newtons. And I'm going to find F net there. Keeping in mind that the net force also includes a direction, because force is a vector. So on our calculators, everybody follow along with me here? Let's use some brackets here. 3.5218489 times 10 to the 22, and the brackets square that, plus bracket 1.984832 times 10 to the 20 newtons, bracket squared. So a squared plus b squared. And then what are you going to do to get the F net value? Square root that. Gives me 3.52 times 10 to the 22 newtons. 3.52 times 10 to the 22 newtons. And then to find the angle, we're going to say theta is equal to the inverse tan of opposite over adjacent, which is 1.98 dot 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 over 3.52 dot dot dot. So second function tan, 1.984832. Go with the unrounded number there, times 10 to the 20, divide it by 3.5218489 times 10 to the 22. Gives me a value, oh, look at that. That's a pretty small angle, right? 0.323. And that would be, we can't really say north of east, right? We'd like to say north of east here, but our frame of reference, north and east, belong to the Earth. And we're talking about space here now, so we just have to label the diagram there. Okay, 0.323 right there. Somebody asked me the other day, how do we find the value of G? Like, how do we know that G, big G that is 6.67 times 10 to the minus 11? I said, well, Newton came up with the equation. He described the magnitude of the force by saying F is equal to G m1 m2 over r squared, but he didn't know what G was. He knew that there had to be a constant, he just didn't know what it was. So we enter Cavendish, Henri Cavendish, who devised an experiment that was essentially what I'm about to show you. What I'm about to show you is a bit of a simplification, but essentially the same thing. Cavendish had a string or a thin wire hanging from something, top of a box, the ceiling of a little room. It's hanging from something. And on the end of that thin wire, he has a rod. On the end of that rod, he has mass 1, and he has mass 1. So two masses are the same values. Okay, mass 2 is not involved there yet. Mass 2 isn't into the equation yet. Now, we're going to bring another mass nearby one of these M1s. We'll call it M2, and it's being brought nearby M1. What happens to M1 as a result of this? It gets attracted. Now, not very much, so you have to have some way of magnifying the effect here, but in the end, it does get attracted, and it's brought towards it by a slight amount. We can measure the value of r, the distance that separates them, easily. We can measure the value of M1 easily. We can measure the value of M2 easily. We can measure the value of the force, not quite so easily, but we can still do it. Hey, remember that last time you were at the playground on a swing set? You're swinging nice and high, going as high as you can get, and then you decide you're going to twist the swing set. Hey, twist it as much as you can, and then let it go so you start spinning around really fast. Remember that? You do that, and you know, like even intuitively, even if you don't know why this is the case, you know that the more you twist it, the harder it is to twist it, right? The more force is required. The torsional properties, or the twisting properties, this is what torsion means, twisting. The torsional or twisting properties of the chain and the swing set dictate that the more it's twisted, the more force is required. Same deal here. The more this is twisted, the more force is required. So Cavendish would have known if this thin wire right here twists this much, well, then it must have required this much force. Or if it twisted that much, then it must have required that much force. Knowing the twisting or torsional properties of the string, he's able to measure how much force was applied, how much force of gravity between the two objects was applied by measuring how much the string or the thin wire twists. Does that make some sense? It's kind of like using a spring scale with a spring in it, right? Like, by knowing the stretching properties of the string, you can measure how much force is applied to the spring. By knowing the twisting properties of the thin wire, you can deduce how much force is applied on the thin wire. So that's how he measures force. Now, if you look at the equation that Newton came up with, all we got to do here now is rearrange it. You know what F is. You know what R is. You know what M is. You know what M is. We can solve for G. In Cavendish, as he does that, gets 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Does that make sense? Now, again, a bit of a simplification, right? He wouldn't have done one trial, and it's a little bit harder to find the force and just saying, oh, it twisted this much, it's this much force is required. But that's essentially what happened there. Yeah.